Hey, how is it going, guys? So in this video we'll discuss about this problem LRU cache. So design and implement a data structure for least recently used cache. It should support the following operation: get and put. So get means get the value will always be positive of the key if the key exists in the cache, otherwise return -1. Put key comma value, set or insert the value if the key is not already present. When the cache reached its capacity, it should invalidate or remove the least recently used item before inserting a new item. The cache is initialized with a cap positive capacity, and we have to do both of these operations in O1 time complexity. So let us see how we can achieve O1 time complexity for both of these methods. So the eviction policy that we are going to use is least recently used. I'll try to explain to you what this means with the help of an example. So consider the initial capacity of a cache to be 3 and the cache is initially empty. So the first instruction is put 0,5. As the cache is empty, we can simply put 0,5 inside the cache so that the size becomes 1. The capacity remains 3. Similarly, we will put 1,10 and put T2,20 in the cache. So over here we have the size of the cache as 3 and the capacity to be 3. When we hit the next put statement 3,30, as you know that the current size is 3 and the capacity is also 3. It means that we have to remove one of the node or evict one of the node, and we have to make space for 3,30. So the policy that we are using is least recently used. So the least recently used node in this case is 0,5. So we will remove this thing and we will simply put 3,30 at the head. Now what you can consider is somehow we need to maintain the relative order in which the nodes are getting processed. Correct. So the next statement is get 1. So as you can see, 1 is present, so we will return 10 out of it. And since we are processing this node, we will bring it at the top or at the head, and we will shift the node something like this. So what I mean to say is that we need to maintain the order in which the nodes are getting processed. And on processing a node, remove it from its original position and move it to the head of the cache. Okay, so we need to implement all these things in O1 complexity. Now consider this thing. In here, when I set get 1, it returns 10 and it takes this node and add it to the head of the cache. So it deletes or removes a node from a position and adds it to the head, and it does all this thing in O1 complexity. So which data structure can we use over here? If you think carefully, deletion of a node at a particular index and insertion at the head can happen in O1 complexity only for doubly linked list. So we are going to use doubly linked list in this question. Okay, let us proceed with this example only. So next is get 5. As you can see, 5 is not present. Over here we will return -1 and the order remains same. Similarly, we have put 4,40. So again 4 is not present, so we will evict the last element, that is 2,20, and we will make space for 4,40, and it will be like something like this. Next is put 3,100. As you can see, 3 is present, so we will change the value of 3 from 30 to 100 and we will bring it at the top. Correct, because this is the currently processing node. So what I'm saying is the nodes which are getting processed currently, we have to delete it from its original position and we have to bring it at the top. So we can achieve this thing in O1 complexity in only doubly linked list. One more thing that I want to mention over here is, in this case we are going to use a data structure with hashmap plus doubly linked list. Why hashmap? We know that in hashmap we can get the get and put methods in O1 complexity. And using doubly linked list, we can delete a node at a particular index and add it to the head in again O1 complexity. Correct. So we will be using a combination of doubly linked list and hashmap. So what I mean to say is we are going to use something like this thing. So basically this is your hashmap with the keys K1 to K5, and these are the values which are the nodes. So the hashmap is going to be of integer comma node, where node is the node of the doubly linked list, and we also have to maintain 2 pointers, head and end, or we can say tail. Why do we need it? Because in case the cache size is equal to the capacity and we have to add a node, we have to remove the least recently used node, which will be pointed by tail. So as you can see, as you can read over here, the problem can be solved with a hashmap that keeps track of keys and its value in the doubly linked list. the result in O1 time for get and put operations and allow to remove the node in O1 as well. So let me write the code for this and things will be more clear from there. So first we need to define a node. So in the node we will be having the key comma value. So this key comma value will be provided to us by the put method. Now as you know, in W linked list we need to maintain two pointers, that is previous and next. And let me define the constructor for this. For int key comma int value, we will be having this dot key equals key, this dot value equals value, correct? So now we have to maintain two nodes, head and tail, as already discussed. Head and tail. We have to keep a variable called size as well, and we have to create a map of integer comma node. Let us name it as map. So in the constructor for LRU cache, what we are going to do is we are going to initialize head equals tail equals null, the size to be equal to capacity, and map is equals to new hash map. So as we have already discussed, the map is going to be of integer comma node. This is going to be the integer and it's going to point to the W linked list node. Okay, so let us write these methods. Okay, so the first method is get method. So first for this key we will check whether this key lies in the map or not. That is, if map dot contains key, this key, then we can fetch the node in O1 complexity using this method map dot get key, correct? Now what we have to do is we have to remove this node from its original position in the W linked list, and we have to point it to the head, correct? So what we will do is we will write a method called remove and we will pass this node. We will write this method later on, but what this method is going to do is it's going to remove the node from its current position. Next we are going to use a method called set head and we will pass the node into it, and it will make this node the head. That is, as you can see in this case, when I'm trying to fetch 1, I'm going to return 10, but I'm going to delete this node from its original position and I'm going to put it over here. Okay, so that's what these methods are going to do, and we can simply return the node.value from here. And in case the map doesn't contain this key, it means that this key does not exist in the cache, and we can simply return a -1 from here. Okay, next method is put. So over here again we'll check whether map dot contains key. This means that this key comma value, this key already exists in the map, so we have to update the value for it. We have already seen this in this example. When we have something like this and we are putting 3,100, as you can see 3 already exists as a key, but the value for that is 30. So what we did is we changed the value, we removed the node from its current position and we point it to the head. So that's what we're going to do over here. First we will fetch the node using map.get key. This is again O1 complexity. Once we fetch it, we will change the value for this node to be equal to the current value. Now what we will do is we will remove it from its original position and we will simply say set head node. We will bring it at the head. Else means this key does not exist in the cache. So this is going to be a new node. Now over here we have to check whether the current size of the cache equal size or not. In case it does, we have to remove one node, correct? The cache eviction policy, that is the least recently used node. So how can we get to that node? We can simply call first of all map dot remove, as we know we have a tail, right? So this tail will be pointing to that node. So we are going to remove this node, that is the least recently used node, and the tail, that is end over here, which will be pointing to this. So we have to remove it from both the places, that is from the doubly linked list and from the map. So what we will do is map dot remove tail dot key, and we will simply call the remove method for tail. Correct. In case this wasn't the case, what we have to do is we have to create a new node with key comma value, and we have to put it into the hash map with key equals key, and we have to call set head for this node. Now you might say that we are not calling remove for this node. We are not going to call remove for this node because this node does not exist in the linked list, in the doubly linked list. That's why we are first entering it over here, and then we are calling the set head method, which will insert it in the doubly linked list. So now both of our methods are completed. Now we have to write two more methods, that is remove and set head. So let us see how we can write these methods. First is void remove, and we will simply pass a node to it. So when you're removing a node, suppose we have to remove this n3. So in case I'm removing this n3 node, I have to make a lot of changes. First of all, this n2's next should point to n4. n4 previous should point to n2. In that case, n3 will be deleted. So what we will check is, first of all, if node dot previous not equals to null, then we will say node dot previous dot next equals node dot next. Okay, let me show you again. So if this is the node, then node dot previous is this thing. We have to check whether this is null or not. Okay, in case it is not null, we have to point its next pointer, that is this pointer, to the current node's next. So in this case, n2 will point to n4. What happens when node dot previous equal null? This actually can happen. This will happen when we are removing the head node. Correct. So in that case, what we will do is we will simply point head to node dot next. That is, in case we are removing this node, what we will do is the current head is pointing to this. So we will simply point head to this thing. So similarly, for the forward connection, we need to create a backward connection. So we will check whether node dot next not equals null. In that case, we will say node dot next dot previous equals node dot previous. So node dot next dot previous. So we are checking for n3, the node dot next is this. We are checking whether this is null or not. In case it is not null, we are pointing its previous pointer, that is this pointer, to the n2. So we have to say node dot next dot previous, which is this pointer, to node dot previous, which is n2. Now it might happen that the node dot next is null. This will happen in case a node is we have to remove the last node. So for that, the tail will be pointing to this. So we will remove the tail from here and we will simply point over here. That is, we will write tail equals node dot previous. Correct. So this method is also over. The last method that we have to write is set head, in which we will pass a node and it will simply put it at the head of the doubly linked list. So you can say that if this node, if we have to set this node as head, as you can see, for head, the previous is null. So simply write node dot previous equals null. Correct. Now if I'm adding a new node over here, then the next should point to this node, and this node's pointer is in head. So we will say node dot next must be equals to head. Here we will check if head not equals null. So currently head will be pointing to this node, correct? And we are adding a node over here, correct? So we want this node's previous pointer to point to a node. So we will say head dot previous equals our node, that is node, and then head will be pointing to our node. One more case that we have to check over here is what will happen when we are adding the first node to the W linked list. That is, the W linked list is currently empty. Nothing is there. We are just adding the first node. In that case, the tail is also going to be null. So we will simply point the tail to the current node, which is the head. So I guess that's it. Let me run this code. Okay, so we are getting an error over here on line number 38. I guess I misspelled this method. So this is set head with H capital. Let me run it again. Now we are doing one more mistake at line number 41. So this is a variable, this is not a method. Okay, so let me just check it once. So what we are doing is we are creating a node with key value and node previous next. Then we have head, tail, size, map. Then we are initializing them all. In the get method, we are checking whether it lies in the map or not. In case it does, we are just taking it from the map. We are removing it and we are setting it at the head. We are returning the value, we are returning -1. So this seems fine. What about the put? We are checking whether it lies in the map or not. In case it does, we are fetching that value, we are changing the value, we are removing in the setting. In case it doesn't lie in the map, we have to check whether the size equal size. In that case, we have to remove the least recently used node, which will be pointed by tail. So we'll just remove it from the map and from the W linked list, and we create a new node. We'll put it in the map and in the W linked list. In the remove method, node.previous node equals null. We are setting this as this, head equals this. This also seems fine. In the head method, this seems fine. Everything seems fine now. So let me just run the code. So it got accepted. Let me submit it. So yeah, we got a success. So I know it's a quite of complex problem. So actually I've already made notes for you guys. So you can just go through these notes on your own after this video. So I guess that's it from the video. So in case you have learned anything from the video, you can hit that like button and you can even subscribe to my channel. Thank you.